Hey everybody, just want to go through these equations here again, just like we have in the past, and make sure we get the correct formulas and equations and balanced and all that good stuff. So I had two videos this time, but there are actually three reactions that I have listed here, because that first reaction where we heat the copper 2 carbonate, there's a second reaction there where we test the gas that comes off of that by bubbling it through the lime water. So I put that one on there as well, even though it doesn't really fit into our types of reactions that we've talked about. So, but we'll talk about that one in just a second here. Let's go on ahead and start with the first one here. So the first one here, heating copper 2 carbonate. So when we heat that copper 2 carbonate, as I've talked about before, there's a difference between heating something and burning something. This doesn't really burn, you just sort of heat it up. And when you heat it up, first of all, we're starting with copper 2 carbonate. Remember that 2 means plus 2, and the carbonate, CO3, is a negative 2, so copper 2 carbonate is just CuCO3. And if you recall from the video, that is a mint green solid. And as I was saying, we heated that up. We didn't really burn it. We just heated it up. So that is our only reactant. So you can tell right away this is going to be a decomposition reaction, right? So from this we get a gas, and then the stuff that's left behind in the test tube is looks like sort of like black soot that's left behind in the test tube, if you remember from the video. So that gas we ran through the lime water, and that's this second equation here. When the lime water reaction is the carbon dioxide gas, the reason that lime water turned cloudy is because that cloudiness is a positive test for carbon dioxide. So that gas that comes off of that is indeed carbon dioxide. And then we're sort of left to figure out, okay, well, what's left behind in the test tube? Well, we know law of conservation tells us that everything we start with over here, we have to end up with over here on the product side. So we know that we've got to have some copper somewhere. So you might assume that what would be left behind is just plain old copper, just pure copper. But if you look at it, you can kind of tell that it's not, right? As I said earlier, it's sort of a black soot material. It does not have that reddish brownish appearance that we know copper to have. And so some of you might have figured out that what that actually is that it is an oxide of copper. In fact, it is copper 2 oxide. So the copper still has a plus 2, oxide always has a negative 2, and so that formula then is CuO. And that is that black stuff that's left behind, that black solid that's left behind in the test tube. So that's a little bit of a tricky part right there, but once you figure out that that's not copper, but indeed a copper oxide compound, and if you kind of make the assumption, and this isn't always true, but it's sometimes safe to assume that since the copper is a plus 2 on this side, that it's a plus 2 on this side as well. Again, that's not always true, but it is often true. So this is our equation. It turns out we actually don't need to do anything to balance this, because we've got one carbon on each side, and we've got one copper on each side, and we've got 3 oxygens on the reactant side. We've only got 2 here, but we've got another one over here. So everything is actually already balanced. All right, let's move on to the lime water reaction. So lime water, as I tell you right here, is actually calcium hydroxide. So Ca, calcium, is a plus 2. Hydroxide is a polyatomic ion, OH, with a negative 1 charge. So calcium hydroxide, I need 2 of those hydroxides to balance out the plus 2 calcium. And that is a solution. It's actually what's called a dilute solution. It just means that not very much of the calcium hydroxide dissolves, but enough of it dissolves that when it comes in contact with carbon dioxide, that's the gas that bubbles through it, when it comes in contact with carbon dioxide, it turns cloudy. So when it reacts with carbon dioxide, in other words, it makes this cloudy material. Now, here's the sort of tricky part. What is that cloudy stuff? So, again, we have to kind of think about our law of conservation of mass, law of conservation of matter, which says that Everything that we start with, we have to end with over here. So let's look at what we've got. We've got calcium, we've got carbon, we've got oxygen, we've got hydrogen. Those are the elements that we have. So the cloudiness, I should point out, the reason that turns cloudy is because that stuff does not dissolve. In other words, that's the little hint I was trying to get you to think about here. Think about a possible product that would be insoluble. In other words, would not dissolve. That's the cloudiness that shows up in that lime water when it reacts with the carbon dioxide. And in fact, let me see if I can do this here. Let me back up. I have my solubility rules here. Here we go. So solubility rules are down here. So if we take a look here, pull that up and blow that up just a little bit. And so if we look on our solubility rules, remember the way this works is the 1 through 5 on the left-hand side here. If a compound contains these things, it means it's soluble, it does dissolve. And if it contains the things in the right-hand column, it is insoluble. Okay? Well, one thing that might stand out is this carbonate ion, number 6 right here. So carbonate ion, you probably remember, is CO3 with a -2. It's actually up here, higher up in the on our list here. If I scroll up here, I can find carbonate here. It's right on the top of the +2 list, right? Or excuse me, -2 list right there. So why do I bring up carbonate? Well, if we look at, I'm going to get rid of this stuff here because I want to look at this later. All right, so let's get out of here and go back to here. So if we look at what we've got here, we have the ingredients for carbonate, right? We've got carbon and oxygen. So what is that carbonate ion going to go with? Well, it's going to go with the calcium over here. So that cloudiness is actually calcium carbonate. Calcium is a +2, carbonate's a -2, and so that stuff right there is the solid precipitate that forms the cloudiness in that water when it reacts with carbon dioxide. So what's left over? What's the other product? We've got some other stuff to account for, mainly hydrogen. Well, we didn't get a gas forming like that. Again, you might assume that, well, it's just hydrogen. That's the only thing we've got left over. That's the only thing we haven't used in some way on the product side yet. But I didn't note, there was gas bubbling through the tube, but that came from this reaction up here, right? There wasn't any new gas being formed. And in fact, what is actually being formed there is water, a good old H2O, and that is formed in the liquid state. This would be kind of tough to figure out because, again, this doesn't really fit into one of our categories, one of our 5 types of reactions. It's sort of like a double replacement, but kind of not really. Because, the calcium and the oxygen here maybe sort of go over here and form the calcium carbonate with this guy, and one of these oxygens maybe goes over here and forms water. Again, not quite. It doesn't really fit one of our reaction types. I've made this kind of a mess here again, but as it turns out, we don't need any coefficients here either. We've got one, let me change colors here real quick. We've got one calcium on this side. Ooh, that changed every color, didn't it? So let's not do that. We've got one calcium on this side, one calcium on this side, one carbon over here, one carbon over here. 3 + 1 is 4 oxygens, 2 oxygens here, and 2 more oxygens here. So 4 oxygens there, and 2 hydrogens here, 2 hydrogens here. So everything is all balanced up. So no coefficients on that one either. All right, let's move on to this last one. This last one, again, we start with 2 ionic compounds. Hopefully at this point you're starting to recognize these equation types, these reaction types. And what I mean by that is that as soon as I see that I've got 2 ionic compounds, right? Iron 3 nitrate, that's iron with a +3. Nitrate is a -1, so it takes 3 of those guys. Remember, of course, that was in solution. And the sodium carbonate Na is a +1, sodium's a +1, carbonate is a -2, so it takes 2 of those sodiums. That was also in solution, AQ. And what I mean by, like starting to recognize those types of reactions, when we see something like this where we have 2 ionic compounds in solution, right away you should start thinking double replacement. And in fact, that's what this guy is going to end up being. It's going to be a double replacement. So what that means, of course, is that the iron and the sodium basically trade partners. Or you could think of it as the nitrate and the carbonate trade partners as well. But either way, so now that means the sodium is now with the nitrate, and we're going to balance up charges here. Sodium +1, nitrate -1. And the iron 3, it's going to keep its charge, is now with the carbonate. So now we got to balance charges here as well. Iron +3 and carbonate -2, so that 3-2 thing that we see all the time, that means we need 2 of these guys and parentheses around this and 3 of these guys. Now, the big question, well, 2 things. First of all, we have to balance it. And secondly, we need to figure out what the states are for our products, right? So one of these guys is the precipitate. If you remember, there was a picture of what this looked like at the end, and it has sort of an orange kind of globular precipitate that sits in there and settles on the bottom eventually. One of these guys is the precipitate, and the other one is dissolved. So we got to figure out which one is which. So let's go ahead and do the balancing first. So let's see here. We've got 2 irons on this side, but only 1 iron on the reactant side, so we put a 2 there to get our 2 irons. Let's see, we've got 2 sodiums right here, but only 1 sodium right here. But a bigger problem is we've got 6 nitrates, right? 2 times 3, 6 nitrates. And if I'm going to end up with 6 nitrates over here, then I'm going to need a 6 right there. Okay? And then, of course, that gives me 6 sodiums. Well, that means I need a 3 right here in front of this, Na2CO3. So that gives me 6 sodiums. That also gives me 3 carbonates. Well, I've already got 3 carbonates, right? I had 3 carbonates when I had to balance out those charges. All right, last thing is here to figure out which one of our products is the precipitate. So I'm going to back out here and go look at those solubility rules again. Here we go. And let's take a look here. So if we look at our rules here, there are a few rules that apply here. One rule is number 1 right here. Oops. I don't circle it very well. Alkali metal ions. Sodium is an alkali metal. Remember, first column is alkali metals. First column of metals is the alkali metals. What we're trying to figure out here, we've got sodium nitrate, right, was one of our products, and iron 3 nitrate, iron 3 carbonate was the other product. There we go. So we're trying to figure out which one of these is dissolved, which one of these does not dissolve. Well, according to the solubility rules, anything that contains an alkali metal, like sodium, is probably soluble. Look at rule number 3. Anything that contains the nitrate ion, probably soluble. So probably a pretty safe bet that this guy is the AQ, that's the soluble one, and that iron 3 carbonate is our precipitate. But there's even another rule that will also apply, and that is that rule we looked at before about carbonates. Carbonates are usually insoluble unless they have a Rule 1 exception, which Rule 1 was an alkali metal. So if it contains an alkali metal or the ammonium ion, it might be soluble, but iron 3 nitrate is not soluble. So in fact, that is our precipitate. So let's go back and finish that out on this guy over here. And okay, like I said, I've kind of made a mess of this here like I usually do. But to finish this out, this guy is a Q, and this guy is solid. All right. Think that does it for these three equations and those two videos. That's it for today. Have a great weekend, and I will talk to you in one form or another